Okay, good morning, good afternoon, and good evening for the global audience for this panel in the series of the Networking Channel event co-sponsored by Empower, Power Project Office, and ACM SIGCOM. Very excited to introduce this topic today and our esteemed panelists. The topic is emerging trends in AI, ML, and implications for networking research. Just before I kick it off, just some logistical questions and FAQs. So this panel is being recorded. It'll be available on our YouTube channel. It'll be available on the website, networkingchannel.eu. And we will be collecting the questions as you hear the panelists speak and react to the questions we've already posed as part of the abstract using the Zoom Q&A feature. We also have a Slack channel that's co-sponsored by ACM SIGCOM, where we'll be monitoring for questions, comments, and reactions. Without further ado, I'd like to introduce the panelists and then hand it over to the panel moderator, starting off with Dr. Nageen Himayat, who's a principal engineer at Intel Labs and also a technical co-sponsor for this particular panel. Dr. Sujata Banerjee, Senior Director of Research at VMware from the US, Dr. Somdeb Majumdar, Head of Intel's AI Lab in the US, Dr. Dario Rossi from Huawei in France, and last but not least, Dr. Dan Pai from Tsinghua University, as well as Director of AI Ops Lab in China. So Nageen, over to you, and really excited to see this panel get kicked off. Thank you everyone for being here.
Let me just share my screen. Can you guys see the screen and can you hear me well?
Yes. Yes.
Okay, so let's just get started. This is a panel on, as Abhimanyu mentioned, on how AI and machine learning interacts with the communication networks. And I'm going to just present one slide to set the panel up. So this is we are going to look at both angles on how AI interacts with communication networks. So the first side of it, or the first point of it, is that AI can be used to improve the performance and the operation of communication networks. And the reason we are using this technology is that communication networks are getting more complex, as we are aware, and they're increasingly supporting very diverse requirements and services. And some of these services are very mission critical, such as self-driving cars and so forth. So really, there's a need to come up with new tools to address this complexity and automate parts of this network. And some people believe that this may lead to a totally new way of designing communication networks, which may simplify the design cycle as well. On the other hand, as networks become more complex, they are also providing an opportunity. They're getting they're getting more powerful in the sense they're capable of sensing, computing, as well as communicating. So there is an opportunity to take the compute much closer to distribute the compute across the network and take it much closer to where the data is generated, and basically allow for AI services to become more pervasive and contextualized according to the local context. So there's a lot of opportunity to synergy to kind of apply AI for networks and networks for AI, but there are lots of challenges that we face in introducing this. Some of the challenges are because of the wireless networking, or basically communication networking environment itself, because these networks are mission critical, as we pointed out. And also they're very dynamic. Environment changes very frequently. So traditional methods of AI may not be directly applicable, and you may need to modify in terms of how do you learn and adapt quickly, how do you learn from very small amount of samples and so forth. And some of the issues arise from the issues that AI models or AI technology faces today. As we are aware, there are lots of challenges that have been pointed out in terms of security, privacy, as well as the resilience of these models, especially if you're trying to introduce them into mission critical networks. If you're trying to use the networks for computing AI solutions, then the other challenges which arise is that you no longer have the luxury of throwing lots of compute power as you would do in a data center, and you're operating in a very resource constrained environment. Also, you do not have the luxury to have human beings annotate the data for you, which is very essential. So things like self-learning becomes important, and then all the other issues of we are operating at the edge in a distributed fashion, so security, manageability, and so forth are of an issue. So these are just samples of what the challenges could be. We have a very diverse panel, so I just want to introduce the panelists. I think Abhimanyu already introduced it. So each panelist would give their prepared remarks for 6 minutes, and then we will go into Q&A. We might start with I might start with some questions, but really we would like this panel to be interactive. The panelists have the opportunity to ask questions, as well as, we'll have audience participate. And I just want to say that we have panelists which are drawn from AI experts, networking experts, as well as academia, industry experts, and diverse geographies. So we do really expect that it will be a good discussion. So please participate. And with that, I will hand off to our next panelist, Dr. Banerjee, and stop sharing.
Thank you. Let me share my screen. Can you see it? Yep. Okay, great. Thank you, Nageen, so much. And thank you for inviting me to speak at this panel. And just to start things off, I hope everybody is doing okay across the world in this ongoing pandemic. Hope you and your families are staying safe. So I wanted to start off by mentioning the journey that we have been on. Networks have been on this transformation journey towards getting highly automated and getting more operationally efficient, making it easier for new applications to take advantage to be supported. And I see this new chapter with the AI and machine learning capabilities on this sort of supporting this journey. So in some sense, we've been on this journey. Here's another set of tools and techniques to help us achieve the goals. The other thing that I wanted to mention is that we are seeing a number of trends that are coming to a confluence right now. And AI and machine learning is just one of them. And we should really look at the advances in AI and machine learning in this broader context of the networks are getting modernized with new hardware, new capabilities, new programmable elements. The next generation wireless is getting fused with cloud and other technologies, and there are new real-time applications. There's a lot happening at the IoT and the IoT environments, and particularly in the edge. And how we apply AI and machine learning across these different environments is key. So it's not a one size fits all or one solution fits all kind of an environment. And we are on our way. There are many smart network components, individually that have come up in the last few years, and many of them are using techniques like reinforcement learning and other techniques to be able to, make the wireless link adaptation more smart or congestion control more smart. But these are all happening currently in isolation mostly, and obviously how they interact with each other is key. How we come up with sort of joint optimizations or single optimization, that is key as well. So we have quite a way to go. So in the few minutes that I have, there's a lot to unpack, but I would like to focus on just a couple of questions. And so one of the things that I feel like we really need to think about in this new environment is the network operating correctly? And can we verify the correctness? Is it robust? Does it make fair decisions? And in some ways, we have, collectively in the networking research community, a lot has been done on verification. Troubleshooting, debugging, these things tend to be problems even today. And the question is, as we introduce new technologies like machine learning, are we making it harder to debug? Are we helping the debugging process? And this is something really important. And the other thing that is important to think about is, what's the impact of a wrong decision? Do you cut off somebody's access? Do you, have lowered performance, unexpectedly? And something that I've labeled as, is it the ability to sort of make a mistake in recognizing a cat versus if it's, if you miss a tumor versus the stop sign example that Nageen showed, the impact can be quite severe depending on what decision is made. And this is something to reason about. The other thing that you'll hear, I think, all of the panelists talk about is the whole training process and the real world need to be aligned in some way. Data does drift, our workloads change. A lot of the training is being done on simulation environments, and reproducibility is something that our community has been working on for quite a while. What are the circumstances under which the transfer learning happens or it doesn't happen? And so this is something really key. And one of the exciting things is that the ML community has been looking at some of these problems for a while. And now there are new tools that are coming up to verify machine learning models, particularly things that have been opaque for a while, like deep learning networks. And the sort of graphic on the right is to depict how you can take a network, a neural network, which you can now formally reason about, and you provide a set of network inputs, and can you prove that it stays within some amount, some sort of boundaries? Can we basically assert that when the inputs are now different, inputs drift, can the model still satisfy some of the constraints that we have provided? Now, the tricky bit is both the input and the constraints have to be specified by network experts. And this is where we need to jump in and be able to provide what is the intent. We've been working on intent-based networking for a while, but what is the intent in this context? And so reasoning about what the network has taken decisions on, explaining these network decisions, and these could be, why did an access control was applied? What are the rate limits? Why did the rate limits change? And so on. And some of the things that we have to think about is these large complex models are often harder to explain. And so simpler models, decomposition of these large models into simpler models may actually help in improving explainability. And finally, we have worked a lot on trying to get the humans out of the loop, but maybe this is one area where we want the humans to be back into the loop because of some of the decisions that need human intervention. I know I'm running a little bit short on time. The second question that I think I feel like it's really important is, what is the cost of getting a highly accurate model? And a lot of the work has been focused on getting higher and higher accuracy. This has tremendous burden on the infrastructure, both on the compute side and the data side. And so sustainability and the carbon footprint of all our solutions is really important. Things like supervised versus unsupervised learning, the labeling effort that needs to go into the supervised efforts is really high. And is it even possible for us to label some of the data that we are involved in, the operational data? And so we need to think about unsupervised techniques in order to reduce this effort. And looking at this holistically, the economics of machine learning ops, we need to be able to measure it. And it's not just about how much is my inference cost. It's about what did it take to train my model? What did it take to retrain my model? Am I continuously retraining because of the data drift issue? And those costs are not easy today to actually bring in. And I'll stop shortly with this. There are some exciting emerging approaches around a lot of resource efficient algorithms where you can split your big model into, maybe a hierarchical set of models. You have at the highest level a coarse-grained model, which trains on the entire data. And then you have fine-grained model, which look at specific data sets, which are tuned for a particular expert decision. And these are the kinds of things that reduce the overall overhead. Model and data distillation, what should the model learn and what should the model not learn? Can we do with less training data? These are kinds of techniques that are all emerging, and we are using them in some of the work that we are doing. And finally, integrating existing knowledge. As the community as a whole, we understand, queuing behaviors, for example. Those things perhaps don't need to be relearned, and so can we integrate these knowledge directly into a model without having to train it to learn that. And I'll stop here. This is a great opportunity for multidisciplinary research, and stopping with a quote from Jen Rexford is always good. So I will pass it back to Nageen for the next presentation. Thank you for listening.
Thank you. Thank you, Sujata. So the next presenter is Somdeb from Intel Lab.
Thanks, Nageen. Let me try to share my screen real quick. Can everyone see my screen?
No, not yet. Here we go. We're good.
Awesome. Okay, great. Yeah, thanks, Nageen and the networking channel for inviting me. This is clearly a very going to be a very interesting discussion. And I also want to sort of echo what Sujata said. I hope everyone stays safe in the current scenario in the world. I want to talk a little bit about networking for AI, and I'm glad I'm coming after Dr. Banerjee's talk, because I think in terms of what we do at AI Lab at Intel, we really are sort of a general purpose AI research lab. And we interact a lot with networks, like everything from the sort of multi-node chip interconnects all the way up to grand scale federated learning across distributed data sets that are physically separated overall. And so one thing I wanted to point out, and I'm sure that anyone who's attended any kind of any of these AI seminars has seen sort of the progression of how large these networks have gone. So I wanted to take you back to 2012, when supposedly we came out of this whole AI winter, and this was state of the art. So before this, we couldn't even reliably distinguish between cats and dogs and that kind of what's considered probably primitive in today's AI world. And you see AlexNet, which was one of the sort of groundbreaking applications of deep neural networks back in 2012, was already at 60 million parameters. And even then, it had to take 5 guesses to do simple things like to distinguish mushrooms from cars and leopards. And fast forward to today, or actually last year, this is in fact a small network by today's standard. This is what AI can produce. So stare at this paragraph for a moment. This is generated completely artificially by GPT-3, which has close to 200 billion parameters. And like I said, as we sit here today, this is actually a 1/6 of the biggest network that's available out there, which is, I think, switch transformers. That's something like 1 trillion parameters. So that's a journey that we've gone through from 2012 to 2020. And just to keep this in perspective, this is sort of how the training compute requirements have moved, just in terms of the logarithmic scale and the exponential scale of increase in how much compute is needed for training these massive networks. And immediately you see a problem from a network, or a challenge from the networking point of view, is how do you train these massive networks? Clearly a single node is not enough to train them. Do you distribute them? Do you model parallelize them? Do you data parallelize them? How do you aggregate all the parameter updates for these massive networks across different nodes, and what it means for data movement between nodes, right? So right there is a massive memory bottleneck problem. And exacerbated by this this memory explosion in memory and compute requirements is the fact that the hardware hasn't really kept up. Like if you look at the AI hardware memory growth, it's roughly of the order of twice every 2 years. Whereas if you look at even something like transformers, which is a modern sort of alternative to, or modern evolution of where convolutional neural networks were even 2 or 3 years ago, it's grown at a staggering rate of 240 times per 2 years. So this is clearly unsustainable and presents a lot of interesting opportunities and challenges as well. So what are some of the networking challenges? And I point this out as really a very small subset. In our lab at Intel, we work on each of these points, each of these sort of aspects, and then some more. But some things to sort of maybe stimulate your thinking is, how do you train in a distributed fashion from distributed? Do we have to train distributed? Like once these networks become this massive, there's no training on a single GPU, right? How do you deal with the memory bottlenecks, especially as we think about edge devices? Even forget training, if you're trying to deploy one of these trillion parameter models, you obviously cannot do that on, let's say, a mobile platform or a robotics edge device, right? So how do you compress these models? And Sujata talked a lot about distillation and compression techniques and things like that. Those are all very, very active areas of research. Data security is a very important parameter as you're sharing data across these distributed nodes. How do you make sure that A, you encrypt the data, and B, hopefully you don't have to decrypt it when you're operating on the data. So this whole area of homomorphic projections that allow you to take some of these, to deploy some of these machine learning algorithms on the encrypted domain itself is again a very hot area of research. Can we even train on the edge? Is that even a possibility? Maybe in some sense we could do lifelong learning. There's plenty of papers that have been written on this topic, but it's still not clear how you deal with new scenarios that the old model hasn't seen before. And a very sort of emerging area that I've seen personally become extremely hot over the last year or two is hardware-aware models, and to the context of this audience, network-aware models. So can you actually train these models with the objective of optimizing on some network congestion objective or some hardware memory constraint and things like that? So I give an example here of something we're doing on the hardware-aware models. One common problem is you have this massive, let's say, GPT-3, and you want to deploy it in multiple scenarios to different hardware targets or network targets that have different constraints, right? And so what you don't want to do is go and retrain and retune these networks for every little hardware target that you have. And so we've been working on this sort of train once and think of this more of a sub-network search. So it becomes a search problem rather than a learning or training problem, where the goal is to train a mothership that is good enough in performance that you can find highly performant subnetworks that you can then deploy without any further retraining into one of these target hardwares. And so when I think of the opportunities these present, some of these things that we're working on are obviously when it comes to networking system, we think about how it can help this final AI product or AI use case. And one thing we've been working on over the last couple of years is multi-agent collaborative systems in the context of robotics. We think a lot about, and by the way, when I say collaborating systems, the state of the art today really doesn't take the network into account a lot. A lot of these are assuming some amount of observability on the parts of the agents that are collaborating. So an emerging sort of area of research is now if you allow them to communicate, whether peer-to-peer or within some constraints of overall bandwidth or capacity, then A, can you improve their performance, and B, can these agents autonomously discover new ways of communicating, maybe a new language of communication? So that's a very exciting area of research that we're looking at. Some of these other ones, in the interest of time, I'll skip. I want to talk a little bit about debuggable AI. I think Sujata pointed out as well, and I think this is very important. You'll hear a lot of people talk about interpretable AI and explainable AI, and I tend to take a little bit of a skeptic's view when I hear words like explainable AI, because it goes into a lot of semantic confusion. I'd rather think of these as the goal being to have a debuggable AI. I don't care so much if these are human-like, but I do care that the solutions that are coming out of these training mechanisms are debuggable by a human. And so here's an example of a paper we published last year where we were working on multi-agent collaborative systems on a Google soccer platform. And we used a reinforcement learning framework where typically these networks would be trained using a reward function or some kind of an objective function that a human defines. So the way we transform the problem is they say, hey, let's say there's no universal reward that's defined. Let the system figure out what's a good reward function. With one catch, the reward function has to look like a Python program. And so we constrained the problem in a way that took it from a lot of these examples actually train neural networks to predict objective functions. So we took that problem, turned it on its head and said, we don't want a neural network coming out of this whole thing. We want a symbolic regression tree that you can unroll into some kind of a Pythonic or a programmatic tree. And that worked really well. We could actually discover extremely complex strategies from scratch. And some of those objectives could actually be rolled out as, like you see, simple functionals. So just to conclude, at Intel AI Lab, who we are about 50 machine learning enthusiasts with the two core objectives of understanding the fundamental representational properties of modern ML systems. We need to do that in order to optimize them, and also solve these massive scale problems using the best of new and old AI. So we're not married to deep learning. We do take a lot of ideas from symbolic AI, from rule-based learning, and we try to bring the rigor of deep learning into some of these old AI for robustness and generalizability. And like I mentioned earlier, we work on all of the challenges and opportunities that I just mentioned. And finally, these are all our collaborations. As you can tell, as a research lab, we collaborate extensively with academia and other industrial research partners as well. That's all I have.
Thank you, Somdeb. We'll pass it to Dario Rossi from Huawei.
Okay, thanks. Let me share my screen and go to the presentation. So hope you see it. So
you can see it.
Yeah, so thanks. So first of all, thanks very much for inviting me. It was already very interesting listening to the previous two presentations. A lot of things resonate, so I'm looking forward for the discussion next. So let me just tell briefly that while I'm in Huawei now, I spent a long time in academia before joining. And one of the reasons why I joined Huawei was because I was excited not only to keep working on AI, but also to really turn AI into something that would be used for real. And this is truly the true moment where these things can happen. And Sujata was already mentioning that in order to be successful, you need to have an interdisciplinary set of expertise. And of course, in Huawei, there's a lot of people that are working on all aspects of AI. So we were mentioning before GPT-3, there are people working on LP. There are people that are working on more theoretic AI. There are people that are working on AI applied to basically everything, because we are a company of 180,000 people. And me, I'm representing the AI that is interesting for the network. So I want to start by starting the discussion by saying that we have two sets of people working in the lab. So people that understand the network, so domain experts that have already been used AI, as well as people for which the network is deep neural network, for instance. So AI expert and computer vision that are putting their passion applied to network use cases. So we start there, but we always keep also working on dual stacking, for instance, our techniques on image field. But I want to start here, not by starting on the techniques, but by starting on the problems. So the problems, for my mind, is that, like we were saying before, the network has become autonomous. And the reason for making the network more autonomous is that you want to remove the human from the loop. Humans create 95% of the problems. So they are involved in 95% of the operation and create 75% of the problems. So if your techniques are good enough, there's a benefit for indeed applying it and removing the human from the fast loop. But I also totally agree that we still need to keep the human in the slow loop for verification, for a number of, for helping so the AI is helping the human, is not substituting the human, and will not for a long time. And so right now there's a situation that we face, but that's a very good opportunity for doing so. And if you think about what are the scenarios, well, right now, a decade ago, the software was eating the world, and right now the software is AI software. And so if you think about what is digitalization, it's basically meaning that you have now a lot of a multitude of different industry segments that are now using the network in a more basic fashion. And network now means basically the extension of the IP network. You can imagine from transportation, government to healthcare. All of these different industry segments have different requirements. And in Huawei, we have basically three solutions, which are campus network, data center, and wide area network, that are solving all this, that we can cast these different industry segments to. Now, underlying that, there's a single technological solution that is relying on 5G, the fixed 5G optics, and the Wi-Fi 6 as a substrate of intelligent IP, on top of which we have the incarnation of the autonomous driving network. Now, you can think that if IP was bringing basic connectivity services, now the new intelligent IP is bringing evolving services, and this is through indeed the AI. And as it was mentioned before, this is becoming possible because now the network, the computing, and the storage are blending. And so now the cloud becomes an opportunity to both bring AI to the network and vice versa. So I want to go with just one additional slide to bring a little bit more what is network AI in Huawei. So what is the high-level architecture? There's a 3-layer architecture where you can see here on top things that are basically running on, and I'm just putting a pointer so that you can see better where I'm focusing. So here you have the classic things which are running on the cloud, like for instance, the training that we were discussing before of large models. Then you have something which is closer to the deployment, which is the controller engine, which is someplace between the cloud and the edge, which gives a complete network-wide visibility of what is happening. And so it's very useful for controlling, debugging, and troubleshooting. And then you have, of course, the devices, which are really beyond the edge, so in the fog or in the mist or whatever you want to call it. So really in the devices. And of course, you have a huge heterogeneity, and all those different pieces need to be glued together to make this more useful. So I was listing here a number of opportunities and challenges when you look at what the network can do for AI. And for instance, we were discussing earlier federated learning. When you want to train this monster model, of course, you cannot rely on a single GPU. You cannot even rely on a single TPU. You cannot even rely on a board full of TPUs. And so we have indeed very large monster in which you need a lot of algorithmics. And over there, also the network can help, for instance, by changing the way in which you interconnect these devices, by changing the way in which you schedule in a multi-tenant scenario, you can make this workload more efficient. Of course, when you are looking into a network kind of scenario where you want to deploy a model for the network, then you need to take into account that there's a huge variability, for instance, of different vendors. And so transfer learning and generality of the model was already something that was mentioned. And everybody was already mentioning that general is beautiful, but there's problems. And so you will want to go to for something more specific, keeping the accuracy, but reducing the size and complexity. And so here you have very specific problems of quantization, distillation, and so on and so forth. So that's as far as what is happening in the cloud, sort of in an offline mode. But then you go into something which is more online, probably not a very fast time scale because you're still not exactly in the device, but you are in a network-wide control. And so here you have large-scale data-driven problems. You also have explainability. Somdeb was mentioning XAI, it's a problem. And indeed, XAI is not only explaining the AI technique itself, but also explaining to the human that are going to be using it. And so over there, you need to something that is very specific and not only unsupervised like we're using, but also semi-supervised to be useful for the final user. And last but not least, very interesting, when you go to the very fast time scale, you might have a very tiny device, which are not very energivore, so they're not consuming much power, that are very efficient to bring this operation in a very fast and energy efficient way. But you may also face, for instance, having a very resource constrained platform like only ARM, for which you probably will not be willing to use very deep models. And so here the problem of how do you do real-time inference and control, and the problem of data drift that was mentioned before is that it's going to force you to do incremental and continuous learning. Particularly the labels, so how to do self-supervised learning and how to make the model self-aware, so knowledgeable when they're no longer working in a seamless fashion. And so here, the faster you go in the task lay, then the more you need to basically remove the human in the loop. Now, I know that I could spend 1 hour on this slide, so probably I will skip. I'm going to stop here. Thank you, and hands on the mic to the next speaker.
Thanks a lot, Dario. I think you did good on time. So we hand it off to Dan Pei from Tsinghua University.
All right. So can you see my slides okay and hear me okay?
Yes.
Yes. Thanks, Nageen, and thanks for inviting me to this panel. I think the previous panelists have provided pretty comprehensive view on the panel's topic. And in my presentation, I will just provide my view on some specific questions that are commonly asked in this domain. And by summarizing the lessons that I learned based on the my past few years research on failure detection, failure diagnosis, and failure prediction. Okay, so one of the commonly asked question is that, all those operators have the data for our networking research, and some, researchers, especially those in the academia, don't have access to the data except, when they collaborate with the operators, right? So, so that's a common problem that faced by a lot of researchers. I work in the industrial lab before, and I now work in academia. I know this pretty well. So, but in the past, and I have did a couple of things. I did a couple of things to try to provide some help in this domain. One is this algorithm computation. One is this lab testbed. In this computation, I work with industry people and to define some research questions that they are really interested in, and then ask them to provide the specific data needed for this research problem. And then we get some sponsorship and set up an algorithm computation and attract researchers to try to solve this problem and competing with each other. Right, so we have been doing this for the past 4 years, and the result is that we can actually, by this way, we can actually collect enough data for a research problem that both research community, academia and the industry are interested in, and then publish the data along the way. And for example, the data that we published for the 2018 version actually was used by other researchers who are not even participate in the competition, but they use the data to publish their research work. We have been doing this for several years, and the first three for the 3 years data are public downloadable. The second work we are trying to do is to try to build a kind of a representative and live network plus AI testbed that the community can contribute and use. The key property of this testbed is that we need to have some industry grade system so that, and also the traffic need to be realistic, and then the failure pattern should be realistic, and we keep this running, with the traffic, with the failure, with all kinds of things, so that the solution can be developed based on the data collected over there, and maybe plug in the solution and try to solve the problem currently injected by the testbed. Okay, so I think that's a good vehicle. Another, I think I need to speed up. Okay, the second question I try to answer is that, what's the boundary of the current machine learning, and what can we do to deal with the mission critical questions? So I don't have to enumerate all these questions. You can take a look at the question, but my point on this is that we need to use knowledge to glue all the components. Some are AI enabled, some are not, and then clearly define the property and the capability of AI enabled component in the overall architecture. And we try to avoid the pitfall in which we try to use general machine learning algorithm at the bottom as a black box to tackle networking research and operations problem, failure discovery, failure mitigation, and trust me, I tried it earlier and it didn't work at all. Okay, so that's kind of pitfall because there's a huge gap between all this algorithms capability and the problem that we are facing. And so far, AI succeeds only in specific application scenario, in specific area and specific industry. This is not surprising because we want to. If you consider this, we treat AI as a high-level programming language. We need to code some component for the entire system. It's no different from other programming language such as Java, Python, etc. And you just need to keep in mind that the output of all these AI-enabled components are probabilistic rather than deterministic, right? We are not at a new stage where we only facing this kind of non-perfect component. We have been doing this for many years, in the days of fault tolerance network, fault tolerance computing. And so overall, we just need to consider that, we have some AI embedded component, we have some data input, we have some traditional hard logic based component, we have knowledge, and then we use knowledge, indicated by the edge and some of the database, and we design the overall system around each component's known capability and property, including those AI enabled one, and then glue the component using knowledge. Okay. And in terms of the technology that may help our networking problem, my point is that we need to keep track of the latest advancement of AI technology and try to fully utilize them. That overall we enable a better machine-human hybrid architecture. And in the past, I've tried active learning, transfer learning, and sample learning, and knowledge graph, and each of them is helpful. I just I try a very quick example, try to use this time series anomaly detection problem as a motivation, right? So we have diverse metrics and we have diverse anomalies indicated by the red points on this curve. We try to summarize the pattern and then detect the data point that violate the historical pattern. So anomaly detection. And in the past, we realized that labels are really expensive and often unavailable. Therefore, we need unsupervised approach. Previously, we tried supervised approach, but then we realized, okay, unsupervised approach is almost a must. And then we have hyperparameters, and the hyperparameter affect unsupervised approach performance. Therefore, we still need humans input. And therefore, we have this human input, human in the loop, and active learning can be helpful. And also the training data can be sparse and the data distribution can change in a concept drift. And then we have this, transfer learning to solve, save training overhead and cut and deal with the concept drift. Okay. And the last thing that I want to mention is that, for this kind of a problem over here, we see that, there's no one single algorithm, perfect algorithm that can do this time series anomaly detection perfectly for all this time series and patterns and anomalies. Therefore, we may have to develop different algorithms for different time series. And then if we can somehow profile each time series into some properties, and then if we human build some knowledge, right? So to map the different profile to the classifier that work better for them. And then we can use this in-sample learning and to have multiple algorithms that work with the same time series. Therefore, knowledge graph from human experiment, sometimes we may use mind knowledge, and therefore we can use this in-sample learning and the knowledge graph to complement. Overall, if we can fully utilize the latest advancement in the machine learning community, that can solve a lot of problem in networking at our hand. All right, that's all I have. Thank you for your attention.
Oh, Nageen, you're muted, sorry.
Thank you, yeah. So yeah, thanks everybody. I think this was a very informative set of presentations from all our panelists. We will go to the Q&A session. I think there is a question there, but I will start off the discussion by, I think a number of you pointed to the problem of growing model sizes and also the issue of sustainability. And I was wondering whether you had thought, and people talked about distributing the computations in various ways. I think Dan, you just mentioned you could stitch things together by doing smaller models and combining them through a knowledge graph. So, what in your opinion is going to be a new set of AI technologies would be needed to really do a breakthrough in this area, or you think that the tools that you described would be, or just enhancing the tools that you described would be sufficient? So, no, in no particular order, whoever wants to go first.
So maybe I can take a quick stab at it. So there are a couple of reasons why we want to break up these models. It's not necessarily that you always want to break up a model. Sometimes you want to break up the data as well. So we think of parallelism as sort of two types of parallelism. You think of model parallelism where the model's big, and you think of data parallelism where the model's manageable, but the amount of data needed is large. So I want to address the question from the data parallelism point of view. And there, I think the key problem to solve there is, can we just not use all that data? I think it goes back to, and if you can solve that problem, you've solved so many other things that come with data, like privacy and like, you know, bias and security and things like that. So I think people talk about unsupervised learning a lot, which is, I think, definitely a golden standard to aim for. But I think a lot more sort of manageable set of research ideas fall roughly between supervised learning and completely unsupervised learning. And these are semi-supervised learning problems. There's a lot of data in the wild that's not labeled. And there's, a lot of folks that are working on how do you, we have an objective for a final task that we want to solve. You require some kind of label data for that, right? But the way researchers generally think of these kind of semi-supervised problems, you say, okay, you still have the data that is maybe unlabeled. So, can we use that to describe some auxiliary task that is maybe related to the primary task that you want to solve? But the auxiliary task is often crafted in a way that you don't really need explicitly labeled data. But if you were able to solve that auxiliary task, you would learn enough about the underlying data structure and the features of the data that you want to extract, that with very minimal amount of additional label data, you can actually get performant models on the actual task of interest. So this is a very exciting area of research, and I've seen this in computer vision, reinforcement learning, audio representational properties, NLP. BERT, for example, is a massive network people have looked at semi-supervised learning on BERT. So I think semi-supervised learning will play a big role in sort of helping with the distribution of data itself.
Thank you. Any other opinions?
Maybe one quick, yeah, go ahead.
Yeah, go ahead.
Yeah. I was going to say that a lot of the focus has been on, very high accuracy. And the question is, can we trade off accuracy with some of the resources? It seems like sometimes you get maybe 1% improvement with, say, another 10x of data. And those kinds of, I think, issues need to be looked at much more carefully. But the good news is that a lot of people are looking at that problem. So I expect that there will be quite a few advances in that area, just because we are beginning to sort of understand what's the domain requirement. Can we do with lower accuracy, for example, for certain tasks?
Yeah, that's a good angle. Also, because we're coming from a world where 959 rules, right? So the reliability network must be huge. So is your model 99.9999% accurate? Is not something that you would want to have as a constraint. So to complement that, in terms of technologies, given that I think that Nageen's question was also on what are the possibilities you see in the next technology evolution. So one is binary networks, where you squeeze basically, instead of having things that are 32 bits float, you have bits. Then the question is, can you make that accurate and not only energy efficient? And what is the good trade-off? Well, that's going to depend on your use case. But definitely there's something that can be done. Second thing, but is much more early stage, even the binary network for which there are already realization, is spiky neural network, which are asynchronous. They work like the brain. So there are some startups in China that are already building the hardware for accelerating that. Right now, they are terribly slow. So there's no, and they're not working nearly as good as convolutional neural network, which means they are not even, you wouldn't compare them for accuracy. But given that not everything is synchronous and working, you don't do the same amount of computation. So you might do much less and you spike only some neurons from time to time. So that would be another way to reduce the amount of computational expenditure you would need. And then commenting on Somdeb, yes, another way is also, indeed, there are ways in which, so we also mentioned early few-shot learning, right? I think that somebody mentioned it. We are working on that. I don't know if we explicitly mentioned it, but from time to time, another way of reducing, especially if you are in the training part, is to use less data. And from time to time, you are forced to use only less data because you don't have at all the other. So the environment may force you to do that. That are particularly challenging scenario.
Thank you. Dan, did you have any opinion or? You agree with all the panelists?
I'm okay for now. Yeah.
Okay. Okay, I think we got some useful tips on how to manage this complexity. I think a number of you again pointed to, the value of having distributed solutions, and we know that there is a trend towards, federated learning and distributed training. I think Somdeb, you also mentioned it. So do you think that most of AI solutions would be distributed and training can happen in a distributed manner at the edge, or what's your opinion that this is the way to go, or there will be some mix, or maybe it's not really viable to do everything at the edge. It will stay at the data center. So what's your opinion there? I don't know if anybody wants to take that.
I think it might be impractical to deploy the complete training pipeline on the edge. I'm sort of curious what others think, but I'm trying to think of a scenario where, from where we are today with this trillion parameter systems, to actually practically train them to the level of accuracy that that even matters. I mean, going back to Sujata's point, like even at that threshold, I can't think of a practical way of actually approaching that. I think what needs to happen is maybe think more about continual learning and lifelong learning, because when you train a lot of these models, they are with respect to a certain set of labels or certain set of classes that they're trying to recognize, or that's the objective. But when you deploy it in the real world in a distributed fashion, you get new data, like autonomous driving in network scenarios. You get all kinds of new scenarios on the road, and maybe the network hasn't seen that kind of data before, and it needs to learn a new class, right? So I think a lot more research needs to happen in terms of how do you incrementally add new representational capacities to this network without destroying all of the representational capacities that it has learned already. I think if that problem is reliably solved, then we can think about incremental learning at the edge, which I think is a lot more practical, and at least in the current scenario.
So to
any other
complement
opinion?
that, yes, to complement that, there may be, then I have a question also for Somdeb, which is we're always making reference to GPT-3, but do we actually need it? I mean, in network use cases, right? So if we want to train GPT-3, then we are OpenAI or Microsoft, and that's it. Then for the, so there may be cases where you are forced by legal rules not to share the data, even within the same organization. I mean, if your organization is spread across multiple continents, that's by definition. So we might have that the computation needs to move to the data, but then we cannot put the data in the same place. So one of the reasons why we're doing research on federated learning is that, we don't have so many points like in the edge, like Google, like billion devices. But still, we face problem that, we cannot move the data. And really, we need to pull the data together, because otherwise we don't have enough representation. So we were forced to do that for GPDR plus all other data kind of privacy reason. So there may be cases for which you need it, although you would want really, I would want to not to work on that space because it would make my life easier. But there may be constraints that force you to do that.
Yeah, absolutely. I think that's a good point. I think federated learning definitely sort of tackles one of the obstacles, which is the privacy part. But I think even there, the community as a whole and the ecosystem needs to even think in terms of maybe standards, like federated learning standards, just like we have in wireless communities, right? Like you may have a federated learning set up in company A versus company B, but you still need to agree to a common set of standards where even sharing that federated or the encrypted data, for example, is a thing that's standardized. And that I don't think we are at yet. I think it's something to think about.
Also because you need an incentive model. So what is your value in participating to the coalition? So there must be some sharply value distribution of rewards. So otherwise I'm a big company. I don't share with you, sorry. Exactly. So in this multi-tenant is even worse,
Okay, are there any other comments? Because we do get some questions from the audience finally. So maybe we go to that. I don't know, Sujata and Dan, are you good to go there, or you want to add something to the discussion?
So the only thing that I could perhaps add to what Dario and Som have already talked about is it's not just only about privacy, but it's also resource constraints, right? So it's not possible, and it's wasteful to ship all the data, when you could perhaps even do some simple functions at the edge like filtering. And so I think that it'll be a combination where, we can't do a whole lot of things today, but some of the constraints from the applications, as well as from the data privacy, as well as from the resource constraints, I think we'll have to figure out ways to do it. And there is already quite a bit of work happening in making these models fit at the edge.
Thank you. Dan, any comments from you?
No more, thanks.
Okay, thank you. So let's just take some questions from the Q&A chat window. I guess this is an anonymous attendee. The question is, at what time scales do you think deep learning or deep RL should help the design of networking algorithms, since networking algorithms may require fine-grained, example less than a millisecond decisions, which can be difficult to achieve for general deep model? What should be the good way to go here? Anybody answering that? That question has stumped everybody.
So think about go ahead.
So, the execution millisecond time, the problem is not really the execution of the inference, is more on the time scale of the telemetry. So when you actuate on the network, are you able to get a reliable stream of telemetry that lets you for the next millisecond evaluate if you took the good decision or not? Or you're just changing the condition of the network without being able to measure what's happening. So what we, of course, in order to do millisecond level timescale inference on the devices, you also need to have some TPUs in the edge. Huawei is providing those. We're definitely not trying to do that because it's quite challenging, but still there's a possibility if there's a huge gain for doing that. So it's not completely crazy. It's more difficult to go and build engineering around to make that possible and useful and probably good. One area would be, for instance, if you need to take a scheduling decision for the next frame, that's something that you would do. Many of the decisions that you have probably are not at that level. And if you are in scheduling, why using an AI-based scheduler when you can use good scheduler? So you also would question whether is it really the good fit to use AI, or just you're trying to hammer because when you have a hammer, everything looks like an A. So that's would be my answer to that.
Yeah, I totally agree with you, Dario, about that. I think there are different time scales at which AI and machine learning models and processes will be used. But I think we all have to take a careful look at, is it really needed? Could we just use a simpler heuristic? This is a great question. I don't think we have all the answers yet.
Okay, thank you. I think we can take one more question, and then the remaining questions we can probably answer offline. Okay, so this is leading AI companies like Google are making the solutions open source, example TensorFlow, Keras, and so forth. Is Huawei, Intel, etc., already making data and models open source, or are there plans to make AI for networks more accessible? So I guess it's calling out Huawei and Intel. I don't know what the response is here. Or VMware, for instance, I don't know, I guess.
So since you mentioned Huawei first, let me go. So of course, I mean, we're making also, our software is available in open source. There is MindSpore, which is equivalent stack, which is more thought up for if you want people that are closer to telcos. So that's already a big open source community, which is available. For making data available, that's a question that you can ask to anybody. And the answer is going to be, well, depends on how we made the data. If we made the data through an automated process that doesn't involve any human, we already made that available. So if you go into the recent publication, when we are using testbed to make the data, then we tend to share them. If the data comes from customers, well, there's no way that we're going to get the legal tape, and we're not going to try to make the effort because we know that it's going to be very, very tough. We do like Dan was saying before. So typically, if you're in academia, you can partner with Huawei. So with people with which we are collaborating through NDAs, they can have access to the data. And as long as possible, we're thinking indeed about making at least the models accessible to some extent. Maybe not exactly on the same data, but on some data, some synthetic data for which you can test on properties for reproducibility reason. Of course, they're making the models that are customer grade model, which are in-house, completely open source. It's questionable whether we would be able to do that. But as in our research fiber, of course, that's something that we are already doing to the extent possible. So we can also go further comment later on.
Okay, and maybe quickly, Somdeb, Sujata, do you want to just pitch in before we close and give it back to Abhimanyu? Or maybe you can also answer offline.
Yeah, sure. Just very quickly. So on the Intel Labs side, it's not really that different from any other research lab, whether you think Facebook Fair or Google Research or Google DeepMind. Most of the work we do in labs is open source these days. I mean, I can think of several open source repos that we published in the areas of reinforcement learning, natural language processing. We partnered with, like Dario said, we partnered with our academic collaborators and open source data sets. I'm not aware of anything that's particularly for AI for networks. Nageen, you might know, but I'm not aware of that. But I can imagine that if it's a research topic that is not directly tied to Intel revenues and things like that, that more than likely it would be open source.
Sujata, do you have anything to add before we close here?
No, I'm good. Thank you.
Okay. All right, we hand it back to Abhimanyu.
Thank you.
Thank you very much for all the panelists and the audience. Thanks.
Yes, and just wanted to echo that to all the panelists. Thank you for your time. Bizarre time scales for other people in Europe and China, especially. So thanks again. All of this would be recorded. I know some of you asked for slides. It'll all be published on the website. There are a few open questions. We'll follow up with the panelists and try to get those posted on the networkingchannel.eu website. So keep an eye out there. Just wanted to put a pitch for the next session in 2 weeks. We'll meet again. This is now zooming out from a deeper technical topic from today and talking about digital divide, spectrum, and net neutrality. As you can see, there are some rock stars and pretty influential voices in these topics that are going to be participating, and it'll be organized by Professor Henning Schulzerin from Columbia University, who's a former CTO of the FCC. So up until then, stay safe, and we'll see you in 2 weeks. Thank you to our panelists again. Thank you. Have a great rest of the day. Bye.
Thank you.
Thanks, everyone.
Bye.
Bye-bye.